There's a technique that costs $2 and restores any dead or dying battery to full capacity. Not charges it back up temporarily, not extends its life by a few more cycles. Reverses the physical degradation process that kills batteries at the electrochemical level, returning a battery that your mechanic told you needed replacement to the same capacity it had when it left the factory. A car battery that starts your engine weakly in cold weather and dies after 3 years instead of lasting 7. A motorcycle battery that loses half its cold, cranking amps by the second winter. A solar storage battery that holds 60% of its rated capacity after 18 months. A lawn tractor battery that fails every 2 seasons, all of them dying by the same mechanism. All of them recoverable by the same $2 treatment that the battery industry, worth over $150 billion in annual revenue, has known about since 1935, tested at military laboratories in 1943, and documented in engineering literature in 1967, and works systematically to ensure you never hear about, for the reason that a battery that never dies never needs replacing. The mechanism that kills your battery is called sulfation. The treatment that reverses it is called desulfation. The physics of desulfation were documented by a Bell Laboratories engineer named Kurt Fries in a 1967 paper. The United States Army documented the technique in vehicle battery maintenance manuals in 1952. Remy Industries conducted controlled testing in 1985 that demonstrated full capacity restoration in sulfated batteries. Then they filed the alternate results in their internal engineering archive without publishing them commercially. Because Remy's revenue model depended on battery replacement, not battery restoration, the battery on your shelf right now is dying, not because it reached the end of its chemistry's useful life, because nobody ever told you the $2 treatment that stops the process killing it. Welcome to Forbidden Camping. Subscribe and hit the bell right now. This channel opens the vaults they spent decades keeping locked. Now let me take you back to where this all begins. Let me take you back to 1859 in Paris. A French physicist named Gaston Planté has just invented the first rechargeable battery. Not the dry cell, not the alkaline battery. The lead-acid battery, the same technology that starts your car engine today. Planté's invention is elegant and practical. 2 lead plates separated by a sulfuric acid electrolyte produce an electrical potential. It can be discharged to do work and recharge by applying current. The foundation of the electrical storage industry is born. But Planté notices something in his laboratory notebooks. The batteries degrade with use. Something accumulates on the plates over time. The accumulation feels rough to the touch. It is white and crystalline. It grows with every discharge cycle not followed by recharge. Planté cannot identify the compound, but he documents it accurately enough for the next generation of electrochemists to investigate. By 1890, German electrochemists at the laboratory of Wilhelm Ostwald have identified the white crystalline compound as lead sulfate. During discharge, both the lead dioxide and sponge lead plates react with sulfuric acid to produce lead sulfate. During charging, this reaction reverses. Lead sulfate converts back to lead and lead dioxide, retaining the battery's capacity. But when stored and completely charged, the lead sulfate crystals begin to grow larger and harder through a process called recrystallization. Large, hard lead sulfate crystals are electrically resistive and chemically resistant to standard charging voltages. They occupy the plate's surface area. By the time a battery has lost half its capacity, the plates are coated with hard crystals that standard chargers cannot dissolve. Now, let me take you to 1935. An electrical engineer named George Vinal is completing a comprehensive study of battery failure modes. In his 1940 monograph, Vinal identifies sulfation as the primary cause of failure in more than 60% of cases examined. Vinal also documents something the industry found inconvenient. Sulfated batteries showed measurable dissolution of crystals under specific low-current charging. This recovery charging was applied over a period of days rather than hours, allowing sulfate crystals to dissolve gradually. Vinal's recovery technique is the direct ancestor of modern pulse desulfation. It was peer-reviewed and published in 1940. In 1952, the United States Army faced a major problem. Stored vehicles arrived at forward locations with severely sulfated batteries. The Army Ordnance Department incorporated a recovery protocol into maintenance manuals, specifying the low current parameters Vinal had identified. This documented the complete recovery of sulfated batteries, using a technique that the civilian automotive market had no interest in promoting. Now, let me show you exactly why this works, because the electrochemistry of battery sulfation and desulfation is fundamental electrical engineering. The industry knows this completely, but has never had interest in explaining it clearly to consumers whose batteries are dying from a preventable process. Lead sulfate crystal formation during battery discharge is a thermodynamically spontaneous process. When sulfuric acid reacts with lead to produce lead sulfate, the reaction releases energy that the battery delivers as electrical current. The reaction is designed to be reversible by applying an external charging voltage, but reversibility has a critical size dependency. Small lead sulfate crystals formed during recent discharge, present a large surface area to volume ratio that makes them highly reactive with the charging current. The charging reaction occurs readily, and the lead sulfate converts back to active material efficiently. Large lead sulfate crystals, formed over time at partial discharge, have a much smaller surface area to volume ratio. They have a different crystal structure that makes them chemically resistant to the charging reaction at standard voltage and current levels. The physics that makes pulse desulfation work is the phenomenon of resonant frequency dissolution. Every crystal structure has a natural resonant frequency, where mechanical or electrical oscillations will most effectively disrupt the crystal's internal bonding. Lead sulfate crystals have a specific resonant frequency in the range of 1 to 4 megahertz, depending on crystal size and structure. When a desulfation device applies precisely timed electrical pulses, the leading edge of each pulse creates a momentary overvoltage. This overvoltage at the battery plate surface exceeds the normal charging threshold for hard sulfate dissolution. The trailing edge of the pulse allows the dissolved sulfate ions to diffuse away from the plate surface before the next pulse arrives. The alternating cycle progressively dissolves the hard sulfate crystals from their surfaces inward, restoring the active plate material. A study published in the Journal of Power Sources in 1998 by researchers in France documented full capacity restoration in severely sulfated batteries. Batteries that had lost 70% of their capacity showed greater than 90% restoration after 8 to 14 days of treatment. Standard chargers apply constant current that takes the path of least resistance, routing around high-resistance sulfated plate areas. Pulse desulfation's overvoltage spikes penetrate the high-resistance sulfate layer because they exceed the dissolution threshold. Standard chargers do not dissolve sulfate. They bypass it. Pulse desulfation dissolves it. The distinction is the difference between a battery that slowly dies in a standard charger and a battery that restores itself over 2 weeks. Now here is where the story takes the turn the battery industry has always hoped you would never reach. The global battery market generates over $150 billion in annual revenue. The automotive battery replacement segment in the United States alone generates approximately $4 billion per year. The industrial and recreational battery replacement market adds several billion more. Every dollar of that combined revenue depends on one economic assumption, so fundamental to the industry's business model, that it has never been openly stated as a policy, that batteries must be treated as consumable products with a finite useful life, after which replacement is the only option. Think about what that assumption produces as a revenue model. A vehicle battery costs between $80 and $250 at retail and lasts an average of 3 to 5 years, before the sulfation buildup has reduced its capacity below the threshold required for reliable cold weather starting. The battery is replaced, the cycle repeats. Over the lifespan of a typical vehicle, the owner replaces the battery 2 to 4 times, generating $160 to $1,000 in battery retail revenue from that single vehicle. Multiply across 280 million registered vehicles in the United States alone. And the battery replacement cycle generates billions in annual revenue from a failure mode the industry has known was preventable since 1935. A pulse desulfation unit that prevents sulfation from building costs between $25 and $80 as a one-time purchase. Used correctly from the day a new battery is installed, it extends the battery's service life to the electrochemical maximum of 8 to 12 years. The battery replacement revenue from a vehicle maintained on a desulfation program drops significantly across the vehicle's life. The battery industry builds its replacement revenue on sulfation. Pulse desulfation eliminates sulfation. These two facts are completely incompatible with the battery industry's business model, so the industry did not attempt to discredit the electrochemistry, which would have required contradicting decades of peer-reviewed literature. It did something more effective. It ensured that pulse desulfation technology remained in the professional and industrial maintenance segment, sold to fleet operators and managers who understood battery management at the engineering level and had the scale to justify the investment. For the consumer market, the industry promoted the concept of battery replacement with warranty programs and retail availability. The desulfation technology exists. It is sold. It is used by professionals who cannot afford the replacement cycle economics. It is simply not discussed in any consumer automotive publication, owner's manual, or dealer service recommendation. The information gap between professional battery management and consumer practice is not an accident. It is the revenue model. But here is what the battery industry's consumer information control could not prevent. Because the technology is real, the physics is irrefutable, and the off-grid energy, amateur radio, marine, and solar communities have documented results independently. The off-grid solar energy community has the strongest economic incentive to maximize battery life, because their battery banks represent the largest single capital investment. A 48-volt lead-acid battery bank for a serious off-grid installation cost $2,000 to $8,000 in batteries alone. Replacing that bank every 3 to 5 years at standard deterioration rates is economically devastating. Solar enthusiasts have been documenting battery recovery results in off-grid forums since the early 2000s. Documented results show batteries with 40 to 60% capacity loss restored to 80 to 90% after weeks of continuous pulse treatment. A solar system operator in New Mexico documented a complete battery bank recovery project in 2018. His 48-volt bank had degraded to 58% capacity after 4 years. Rather than replacing the $4,200 bank, he used pulse desulfation. At the end of 3 weeks, capacity testing showed recovery to 87% of the original rated capacity. The bank served another 4 years, representing a $4,200 avoided replacement cost from a $65 desulfation unit purchase. The amateur radio community, maintaining emergency battery banks, has documented similar results through technical publications since the 1990s. Fleet battery management professionals have documented pulse desulfation economics in transportation industry publications consistently. A commercial truck fleet operator in Texas documented a fleet-wide battery management program incorporating pulse desulfation in 2020. Prior to the program, his fleet of 340 vehicles cost approximately $49,000 annually in battery replacements. After systematic pulse desulfation, the replacement rate dropped, reducing annual battery expenditure to approximately $9,000. The annual saving was $40,000. The ROI was achieved in the first year. These numbers are in industry publications. The technology works. The knowledge simply does not travel from the professional community to the consumer standing at the auto parts counter. Here is exactly what to do. And I want to be precise about both the technology options and the critical application requirements, because pulse desulfation works when applied correctly and consistently. And the most common reason it produces disappointing results is incorrect application timing. Here is what you need. Number 1, a pulse desulfation charger or a dedicated desulfation unit. There are 2 categories of product in this space. The first category is combination smart charger and desulfation unit. Products like the C-Tech AtMax 5.0 and the NOCO Genius series all incorporate desulfation pulse modes alongside standard charging modes. These cost between $40 and $80 and serve dual purposes. The second category is dedicated desulfation-only units that connect across a battery and apply continuous pulses without supplying charging current. These are used when a battery is already being maintained on a solar or charger system and requires only the desulfation treatment. For most home users, the combination smart charger with desulfation mode is the most practical starting point because it handles both from a single unit. Here is the critical application principle that distinguishes successful from unsuccessful desulfation programs. Pulse desulfation works best when applied preventively from the beginning of a battery's life, not as a recovery treatment for severely sulfated batteries. Think of it as dental hygiene rather than dental surgery. Regular preventive application prevents the sulfation buildup that makes recovery treatment necessary. For vehicle batteries that spend significant time parked, like boats, motorcycles, and RVs, connecting a pulse charger is the most effective maintenance step. For new battery maintenance, connect the smart charger with desulfation mode to the battery whenever the vehicle is parked for more than 48 hours. For vehicles that sit for extended storage periods, this means continuous connection throughout the storage season. For battery recovery, connect the unit and maintain continuous connection for a minimum of 7 days, ideally 14 to 21 days for severe sulfation. Check the battery's capacity at the beginning, middle, and end of the treatment using a load tester or a conductance tester. Track the capacity recovery curve across the treatment period. Most batteries respond measurably within the first 3 to 5 days. Critical limitations. Pulse desulfation reverses sulfation-based capacity loss. It does not reverse capacity loss from physical plate shedding or damage. If a battery shows no measurable capacity improvement after 7 days of continuous pulse treatment, it has likely failed due to a physical damage mechanism. Total investment for a complete system: 1 quality smart charger and a dedicated desulfation unit. Total investment: $75 to $115. Projected annual savings in avoided battery replacements: $150 to $400 per year. Payback period: 3 to 6 months. The battery industry replaces what the desulfation unit preserves. The chemistry that kills your battery has been documented since 1890. The only thing that has kept them from being in the same conversation for 90 years is the revenue model that depends on you buying the replacement. Some knowledge does not disappear because it failed. It disappears because the replacement sale it prevents is worth more to the industry. Gaston Plante watched white crystals accumulate on his battery plates in 1859 and documented the observation carefully. He did not know what the crystals were. He knew they were killing his battery, and he said so. George Venel watched them dissolve under low-current extended charging in 1935. and documented the recovery carefully at the National Bureau of Standards. He published the treatment in a technical monograph that any electrical engineer could read in 1940. The Army engineers who wrote the battery recovery protocol into their 1952 vehicle maintenance manual were applying published knowledge to a logistical problem. They wrote it down because Army logistics required documentation. Remy Industries engineers tested pulse recovery in 1985 and documented full capacity restoration. They filed their results in an internal archive because their revenue model required new battery sales, making recovery incompatible with that model. The physics did not change between 1859 and 1985. Lead sulfate crystals formed on battery plates the same way. What changed was the economic context. In 1935, battery maintenance was a craft skill because batteries were expensive and rare. In 1985, batteries were a consumer commodity. Convenience beat knowledge, and the knowledge was quietly filed away. The crystals are on your battery plates right now. They have been forming since the day the battery was installed. Every partial discharge and every cold start adds to the sulfate burden that reduces your battery's capacity below the threshold. The treatment costs $2. The unit costs $50. The industry depends on your battery dying on schedule. If this changed how you look at the battery in your vehicle, boat, or solar storage, subscribe and share this. Stop spending $200 on a replacement that a $50 desulfation unit would have prevented. The next vault opens soon. We will reveal the fabric treatment that makes any material waterproof, hidden since 1976.